if I write is that fine? Or do I need to change how big things are? Give me a thumbs up if you can see what I have written here. Okay, cool. Sounds good. All right, here we go. We begin with chapter 10. I will give you an overview and then we'll do some practice problems that I think are worth your time. That needs to go away. So I guess I can start off like this. All right, so for chapter 10, the main things you need to understand. Chapter 10 is very large, and there's several things that are similar. So we need to, yeah, I did see the exam. Indeed, I did. So we need to be able to keep things straight. First of all, the internal energy, delta U, internal energy. So when he talks about the energy of a system, he means this, U, change in delta U, is equal to heat. Q is heat plus work. Work is the energy needed to move something against a force. And the units of heat, Q, are joules. And the units of work are also joules. And the units of internal energy are joules. But what you need to understand is what are the sign of Q and W and what does that mean? Because you're going to need to insert the sign into an equation. So Q can either be positive or negative. And if Q is positive, that's too thick. Down. If Q, that's too thin. You got to wait until I get to what I need because if it's not the right thickness, then it hurts. Okay, I guess it has to be that. All right, I like that. Q, heat. This is old news. If it's positive, the reaction was exothermic. It released heat. So system released heat. We need to be able to define the systems and the surrounding. So I'm going to draw a picture. The circle is the system. The box is the surroundings. You can think of this as being a reaction is in a beaker. That's the system. Beaker with chemicals, reaction. And the entire rest of the universe is the surroundings. But it's the surroundings we usually just say is the lab. And the system is in the beaker. Okay, so if the reaction in the beaker heated up, it's exothermic. So heat goes out of the system. So if heat goes from system, if Q goes from system into surroundings, it's positive. And that's exothermic. And then if, oh, sorry, my bad. True. Negative, I meant to say. Oh no, my eraser is weird. Change the sign. Okay, if the heat goes from the systems into the surroundings, that's Q, that's negative because it lost. So the system released heat or lost heat. I like to think of it as lost. And then if it's endothermic and heat was absorbed from the surroundings into the system, that's whenever the system gains heat, that's positive Q, that's endothermic. So system gained heat. Thank you. Okay, that's old news. You're probably comfortable with that. The other one is work. Work is the energy needed to move something against a force. And when we're talking about chemical reactions, we are talking about atoms making something move. And how can atoms make something move? If you put them in a closed vessel. So specifically, for atoms to get something to move, we need to have that reaction happen in a closed vessel. And we usually give you a description of a piston. And we say that the reaction is happening inside of the piston. And if the reaction is producing a gas and that expands, then the reaction can make the piston move. This is a piston. It goes up and down. So a reaction, atoms can make something move if you enclose it inside of a vessel that is allowed to move and it produces a gas. And so work for you guys is pressure volume work. So pressure volume work. And we need to know how to do this calculation. So work equals negative P times delta V. And delta is always going to be final minus initial. So this is volume final minus volume initial. And the units of this are weird. The units are ATM time liter. Because look, you have pressure, and it's going to be an ATM, time, change in volume, volume is going to be in liter. But you can convert it into joules. And I think it's 101.375 or something. So you can convert this weird unit of ATM time liter into joules if needed. And we're going to do a practice one like that. But let's go back to the signs of W. So we got the signs of Q. If the system loses heat, it's exothermic, Q's negative. If the system gains heat, it's endothermic, Q's positive. Now we need to understand the same thing with work. Bro, that eraser needs to stop being a circle. I don't like that it's a circle. Whatever. That's what it wants to be, then that's what it can be. All right, work positive. Oh, don't be silly. Work positive, work negative. So now we need to think about work the same way that we're thinking about heat. (101.325 joules equals 1 ATM. Thank you. That is the conversion that I needed. 101.325 joule equals 1 ATM time liter. Okay, let's talk work. When is work positive and when is work negative? So work is positive when the surroundings do work on the system. When the surroundings do work on the system, and work is negative when the system does work on the surroundings. So when the surroundings do work on the system, work, surroundings do work on system, work positive. When the system does work on the surroundings, work negative. So when a gas expands inside of a piston, the system is doing work on the surroundings, so work is negative. That's why we have this negative sign right here. Okay, so now let's go to his, and we're going to stop right here and do a practice problem. So Okay, here we go. Let's do a practice problem. This is where you can get this information. I'm in chapter 10, slide 6, explains all of this. Delta E is what he's calling internal energy. That's fine. That's fine. I will stay consistent. Delta E, not delta U, is internal energy. Okay, so let's try a pressure volume word problem because you're going to have one. So when you see words like calculate delta E for the combustion of a gas. So I'm doing question 1 on the practice problems for in the study guide. Calculate delta E for the combustion of a gas that releases this much heat. So here's where you need to understand how to put the signs into the equation. So number 1. It's okay if you can't read the right side of the screen. You have this information. So this reaction is releasing heat. So that means Q is negative. Okay, delta E is going to be Q plus W. But we determine the signs of Q and W by understanding how to put the signs in. So if the combustion is releasing heat, that's going to be exothermic. So this is going to be negative 210.0 kilojoule into its surrounding, and the system does work on its surroundings. So when the system does work on the surroundings, work is negative. So that's going to be minus 65.5. And then you get the answer. Subtract those two, well, add those two values, right? Negative 210 minus 65.5. Looks like 275.5 kilojoule. The change in internal energy. Okay, next, we're moving on. Let's talk about now just Q. Let's just talk about Q now and how to deal with that. We don't have to convert to joules because nobody asked us to. Yeah, so you have to read the problem to know how to insert the sign. We don't have to convert it to joules because nobody told us to convert it to joules. So we had to insert this negative sign and we had to insert this negative sign based on our understanding of when work is positive or negative. Okay, I got to move on. And when Q is positive or negative. All right, we're moving on to Q and the many ways in which we use Q. Q is MCAT. That's the equation for Q. And let's examine MCAT. This is mass, and it needs to be in grams. This is, C can be 3 different flavors of specific heat or heat capacity or specific heat or molar heat capacity, any of those. So this can be heat capacity or specific heat capacity, or molar heat capacity. And the difference is the units and if mass is involved. If mass is not involved, it's just heat capacity, and the unit of C is J over degrees Celsius. Specific heat capacity does involve mass, and the unit is J over gram time degrees Celsius. Molar heat capacity also involves mass, but it has moles instead of grams. So the unit is joule over mole time degrees Celsius. Now, C is how much heat a substance can hold before it itself heats up. No matter what type of C you're dealing with, as you can see, there's 3 types of C. So it's how much heat something can hold before it itself heats up. And if you don't include mass in it, then we just call it the heat capacity. But if you specifically have mass involved, then it's the specific heat capacity. And if you have moles instead of mass, then it's molar heat capacity. They are all used the same way. They are all used Q equals MCAT, except for heat capacity, that's just Q equals CAT. So if we don't have mass anywhere in the question, then we don't use MCAT, we just use CAT. So specific heat capacity is Q equals MCAT, which is the most common one that we use. That's the one that you've been using in lab for 2 weeks. And then molar heat capacity is NC delta T. So we have moles right here, and we have grams right here, and we have no mass on the heat capacity. But I'm going to focus on specific heat capacity because it's the most commonly used one. And then temperature is in Celsius. So that's temperature final minus temperature initial. Now, the ways in which you use this heat capacity are either coffee cup calorimetry, which is what you've been doing in the lab for the past 2 weeks. And the equation expands to 2 different Qs. The heat that the substance inside the calorimeter, which is usually a metal, so I'm going to say metal right here. So the heat the metal lost is equal to the heat the water gained. And you've had a lot of practice in lab doing this calculation, but I'm still going to write the whole thing out. So negative mass, whole thing is negative, metal, mass of metal, times the heat capacity of the metal, times the final temperature that the whole entire system comes to, minus the initial temperature of the metal. That's what that side looks like. And then the other side is mass of water inside your calorimeter times the heat capacity of water, which is 4.184 joule over gram degrees Celsius. That's the heat capacity of water. So don't ask me where that number came from. That is the number that you need to know. Times temperature final of the system minus temperature initial of the water. Okay, let's look at a different type of calorimetry called bomb calorimetry. This is where we do a combustion reaction. This is not where we do a specific heat of a metal situation. Bomb calorimetry, to use this equation in this form, you want to look for the word combustion and heat in the problem. And for this one, the combustion of the reaction or the heat of the reaction is just equal to CAT. There is no mass. So that's bomb calorimetry where we do combustion. Coffee cup calorimetry is either the heat of a metal or a different thing. Now I'm going to bring in enthalpy because I want you to see how everything fits together. So we can also do reactions inside of the coffee cup calorimeter, which is what you did in lab last week. You did 3 total reactions. And if you're measuring the heat of a reaction at constant temperature, it is called the enthalpy, which is delta H. So it looks like this. The heat of a reaction is equal to negative Q of the reaction divided by moles of limiting reagent. And that unit is usually kilojoule per mole. So now let's look at this version of Q, because we only have one Q and there's a negative sign out front that we cannot forget. It's very important. This is equal to the mass of the reaction, whatever that is. You add up all the stuff you put into the calorimeter, the mass of it adds up, and that's what you put for M, times the specific heat of the reaction. And I promise you the reaction is simply going to form water, because we usually do acid-basis reaction. So the specific heat is going to be 4.184 divided by joules over degrees Celsius, because it's just going to be water, times the temperature final minus the temperature initial, all divided by moles of limiting reagent. So both of these, you need to understand how to do both of these type of equations in coffee cup calorimetry. You're either asked to find the enthalpy of a reaction, which requires you to find moles of the limiting reagent, and then you plug everything into Q and you find your enthalpy that way. Or you're asked to do the specific heat of a metal, which is up here. Or you're asked to do a bomb calorimetry combustion problem, which is over here. And now I'll show you what's really going on. Delta H of the reaction is equal to negative Q is equal to negative cat. Don't forget that negative sign. And we don't have moles of limiting reagent in our life. So our unit over here is just joules. Just joules. It could be kilojoules, but we don't have mass involved in bomb calorimetry. Okay, so we're going to stop right here and do some practice problems with this stuff. All right, so let's look at the practice problems and just see if we can identify what equations to use where, and then I'll do one of them. So I'm going to make this bigger for us. All right, so the hardest thing about chemistry, general chemistry, is that they're really hard word problems, right? So let's read the word problems with the information I just gave you and figure out how do we attack them. And then I'll probably show you how to do the bomb calorimetry one. Okay, so the first one, I already showed you how to do number one. That's just Q plus W, and you have to insert the signs. The second one, exactly 10 mils of water. So I'm already labeling my shit, right? Because I'm trying to figure out what equation do I use. So exactly 10 mils of water. Okay, so I have a mass. Yes, it's mils, but the density of water is 1. So that means the mils equals the grams. So I have 10 mils of water at this initial temperature. That's probably the initial temperature of the water is added to a hot iron skillet. All the water is converted into steam to 100 degrees. The mass of the pan is this. What's the change in temperature of the skillet? Okay, so what is the change in temperature of the skillet? So we have a mass of water, we have a mass of the skillet, and we have the temperature change. So Q equals M cat. See if you can figure out how to do that problem, right? So I'm using this because those are the variables that I have. So what is the change in temperature? And what you need to know is what was, how much heat can the skillet hold? How much heat can the skillet hold? And it's iron. So you would need to find the heat capacity of iron. And you have the final temperature. Okay, so you need to look up the heat capacity of iron. All right, number 3, the complete combustion. And I see the word bomb calorimeter. All right, Easy. So I know I'm definitely going to use Q equals cat. So we have the complete combustion of 1.200 grams of cinnamon aldehyde in a bomb calorimeter with the calorimeter constant of this value, that's the C, produced an increase in temperature of this, so that's your delta T. How much thermal energy is produced during the complete combustion of 1 mole? Okay, I will show you how this works. So we know how much heat was gained when we did 1.200 grams of this. So let's plug this in. So the reaction is combustion, which is equal to negative Q, which is equal to negative cat. Don't forget the negative sign. So this is negative. C is the C for the calorimeter. So we've got 3.640. Unit is joule over, oh, they're kilojoule. Unit's kilojoule over degrees Celsius. That's right there in the problem. Times temperature change, which is 12.79 degrees Celsius. Okay, so I will get this value, and this will be equal to the enthalpy of the combustion reaction. All right, so we've got 46.5556 kilojoule per 1.200 grams of this guy, which is C9H8O. But it wants per 1 mole. So we need to convert our gram into mole. And we already know how to, oh, I forgot my negative sign. Very important, especially on a multiple choice test. So I need to keep my negative sign. Right? That negative sign didn't go anywhere. When would the negative sign go away? When your temperature change itself is negative. So when you go from a final temperature that's lower than your initial temperature, let's say you got colder. Let's say you went from 100 degrees Celsius as your initial temperature to 10 degrees Celsius as your final temperature. That's negative 90 degrees Celsius temperature change. That will make the whole thing positive, which would be an endothermic situation, right? So the math will take you to if the reaction is positive, endothermic or exothermic. So if your temperature change is negative, that's whenever your enthalpy becomes positive and it's endothermic. But if your temperature change is positive, which means you heat it up, then the equation makes you keep it negative, which means it's an exothermic process. So don't force the sign, let the math take you there. And don't forget that you have a negative sign in front of your cues of reaction. Okay, so we need to turn it into kilojoule per mole because it's asking us combustion of 1 mole. So we just need to turn our bottom guy into mole. It's in gram right now. So if we have gram on the bottom, that means we need gram on top, and that's going to be per 1 mole. And of course, converting from gram to mole is the molar mass. And the compound is C9H8O. So let's add up the molar mass of cinnamon aldehyde. So I've got 9 carbons, that's 12.01 times 9 plus 8 hydrogens, 8 plus 1.008 plus 15.999 for oxygen. So this boy has a mass of 133.097 gram per 1 mole. And so I would do in my calculator, negative 46.5556 divided by 1.2. Right, so I would do this and then divide it by 1.2 and then times the molar mass. Times 133.097. So delta H of the reaction is equal to negative 5 O trio. Looks like 4 figs is the move, so that's 3-1 actually. Kilojoule. And that unit, so grams will go away and the unit will now be in kilojoule per mole. So that is how you do a bomb calorimeter problem. Number 4 is the same way. We've got, so obviously he has a bomb calorimetry problem on the exam. We've got a mass of ethanol. We're combusting a bomb calorimeter, so there's C-cal, and we have the temperature change. Okay, I'm going to show you how to do number 4. So I'm going to erase the board. We divide by 1.2 grams, Matthew, because we need to convert the value of the temperature change into moles. And the 1.2 grams is how much, so that temperature change was equivalent to 1.2 grams. So the unit of the question was kilojoule per gram, per 1.2 grams. And then we needed to multiply by the molar mass to turn it into moles. All right, so let's look at 4. So Q for the combustion of the reaction. So Q is just equal to cat, okay? So he says, what's the heat? And you need to understand the difference between heat and enthalpy. So the second one is, what is the enthalpy of the reaction? Well, that's equal to negative Q of the reaction, which is equal to negative C delta T. So there's a difference between Q and delta H. So now let's plug in our numbers for A. He's got the calorimeter. C is 4.368 kilojoule divided by degrees Celsius. And then the temperature change is 6.804 degrees Celsius. So degrees Celsius goes away. 4.368 times 6.804. Okay, so the heat value is 29.719872. I don't care about 6 figs right now, but it should be 4. So that, okay, I do care about 6 figs. 29.72. Unit, kilojoule, done. The sign does not come into play. Now he says calculate the heat of combustion for this. So we just enter a negative sign. Oh, sorry. We need to add in divided by moles, divided by moles. So that's what we do here. So we go negative the Q value that we found from above, 29.72 kilojoule per 1.252 grams. So that temperature change, just like before, that temperature change corresponds to that much ethanol being combusted. So that's why the unit is kilojoule per gram, but enthalpy is kilojoule per mole. So we need to turn it into mole, just like we did before. So now we have a molar mass of ethanol, C2H6O. So that's 12.01 times 2 plus 1.008 times 6 plus 15.999. So the molar mass of ethanol is 46.067 gram per 1 mole. And gram goes away. So I take my 29 value without rounding in my calculator, obviously, so I can have the correct answer at the end to put into a exam. Divide, so 29.719872 divided by 1.252 times 46.067. Okay, so the delta H of combustion is equal to negative, and I want 4 sig figs based on the amount in each of the values in the problem. So 1093 kilojoule per mole. That's how you do B. And then writing a balanced chemical equation for combustion is really important. We don't need to do D. That one is not important to us. But we do need to know how to write a balanced chemical equation for combustion. So you have to know that the products of combustion of a hydrocarbon, a compound that contains carbon, hydrogen, and oxygen, which is what we have here, C2H6O. And combustion is oxygen is a reactant. That's the definition of combustion. So we have to know to add that O2, gas, if you want to be specific, makes CO2 and water. If something's being combustion, there's a lot of heat, so the water is going to be steam. Okay, so he says write a balanced chemical equation. So I recommend you balance combustion reactions of hydrocarbons in the order of CHO, as I've said before, just to make your life easier. So we're going to balance carbon first. I have 2 carbons on the left, so I need 2 carbons on the right. And then I have 6 hydrogens on the left, so I need 6 hydrogens on the right, and then I will balance my oxygens. I have 4 oxygens plus 3 oxygens. That's 7 oxygens, not 7D, 7. So I need 7 oxygens on the left, and I have 1. So I need this to equal 6 oxygens, so that's a 3. Done. That's how you create and balance a combustion reaction. All right, number 5 is clearly a coffee cup calorimeter. I'm not going to do it, but you definitely need to know how to do it. So practice that. You've got your masses here. This would be the mass of the reaction. You've got 100 mils, which is 100 grams, because we just say the density is 1. And we have 0.243 grams of magnesium. You add those 2 guys up to be your mass. And then we have the temperature change is here. And we want to know delta H of the reaction. I can't help but do it. I'm just going to do it. I can't help it because you do need to know how to do it. Remember, I'm only talking about things that are actually on the exam. All right, I'm erasing the board and I'm going to do number 5 because I can't help but not do it. Just can't help it. I have to do it. And then we're done with chapter 10. I'm going to show you how to do 6 as well. That's also very important. All right, number 5 is not scary. Let's see what players we have. I like to work with my stuff like this. I like to put all my stuff underneath where it belongs. Yes, yes, that's why I did it. Number 2 is necessary. So the only one to not really focus on for this, 1 was good practice, 2 and 3, 4, but not part D, 5 and 6. So 2 is a little more complicated than the exam, but the concept is still on there. All right, so let's see what the hell's going on with this. All right, so I've got a mass of magnesium of 0.243 gram, and I've got 100 mils of this situation. Oh, look at the density is 1.01. So I need to turn that into grams. So 1.01 gram per 1 mil. So that's important that he gave us the density if he's not going to assume that it's 1, which, that's even more accurate. So this is 101 gram, mil goes away. So that's my mass of HCl. Okay, and then I put it into the acid. So I like to draw pictures on my exam so I don't screw things up. So I've got HCl, 100 mils. And then in there, I put magnesium, 0.243. And it's going to do this reaction. It's going to form hydrogen gas, and hydrogen gas is going to leave the reaction, H2 gas. The exam is equally weighted, chapter 8, 9, and 10. So there's equal number of questions for each chapter. I would recommend going over the in-class PowerPoint if you really wanted to slim things down. Yeah. All right. So the solution, the temperature increased by 33.4. So that's our delta T, right? We don't have a final and an initial temperature. It just tells us the change. What is the value of delta H of the reaction? Okay, we have to remember that delta H of a reaction is equal to negative Q of the reaction divided by moles of limiting reagent. So that's our goal. We're trying to get there. Assume the density solution is this and the specific heat capacity is this. Okay, cool. So we're on it. So this means negative MCAT, so mass of reaction, times specific heat of reaction, which is 4.184. He doesn't have the 4 there, but I'm putting it. Joule over gram degree Celsius times the temperature change, which is given 33.4 degrees Celsius. So now I'm going to put in my mass of reaction where it goes. So instead of just having M, I'm going to put in my mass. So I've got 101 plus 0.243. That's my total mass. So that's 101.243 gram. And then here's the hard part. I have to divide by moles of limiting reagent. Well, I show the math right here, right? I show how I do it. So the density is here. Boom. There we go. Okay, cool, cool, cool. You will be given all the formulas except for combustion. Yeah, so you have to know how to create a combustion reaction, but all the other reactions are given. All right, so here's the hard part, dividing by moles of limiting reagent, right? Like which one is limiting? Well, turn them both into mole. You have to pick a product to choose. So the limiting reagent is the one that limits the amount of product you can make. So let's just turn them into hydrogen and then we can decide which one is the limiting reagent. Unless he tells us in the problem. Let me read it again. Oh, thank you so much. I did not read the problem properly. So we do have an initial temperature and then we have a final temperature. Oh my God, that's my bad. Thank you so much. We do have an initial and a final. I didn't read the problem correctly. Let's fix. So it's not 33.4. It is. Ooh, what are we doing? 33.4 minus 22.4. Okay. All right. And now moles of limiting reagents. So let's turn our HCl into moles. We have 100 So now is find moles of limiting reagent. So we're going to turn our HCl into moles. There's 100 mils, so that's 0.1000 liter times 1.00 moles per 1 liter. And then I'm going to turn it into moles of one of the products just to see which one's limiting. And I'm just going to pick H2. I can pick either product. So there are 2 moles of HCl for every 1 mole of H2. And that comes from the balanced chemical equation, right? There's 2 moles of HCl for every 1 mole of H2. Okay, so this value is going to be 0.05000 moles of H2 if we were to use all of the HCl. So now let's do magnesium to see which one is limiting. Magnesium, we have 0.243 grams, and we need to turn it into moles with the molar mass. And the molar mass of magnesium is 24.305, so 24.305 gram per 1 mole of magnesium. And then I'll turn that also into hydrogen. So there's 1 mole of magnesium for every 1 mole of H2. Point 243 divided by 24.305. So this is 0.009998 moles. So magnesium can make less moles of product. So magnesium is the limiting reagent. So that's how many moles needs to go there. That's how you figure out limiting reagent. Who makes less product? So I just picked hydrogen as the product. So now I need the moles of magnesium to go underneath. So that's just going to be 0.243 divided by 24.305. 0.00999979 moles. Okay, math. So we've got 101.243. That's our total mass of the reaction times 4.184. That's a specific heat of the reaction times the temperature change, 33.4 minus 22.4, divided by the moles. And that's going to be in joules because grams goes away, delta C goes away. So this is joules per mole. And he wants it in kilojoule per mole, which is very common. So there's 1,000 joule in 1 kilojoule. So you need to divide your answer by 1,000. And that's 466 kilojoule per mole negative. So delta H of the reaction is negative 466 kilojoule per mole. I think it should be 46. No, you do not need to understand Hess's law or enthalpy of formation. But you do need to understand bond energy, and enthalpy of formation is very similar. So let's look at number 6 now. Yeah, Hess's law isn't on there. All right, I'm going to erase the board. And I'm going to go back to the whiteboard to show you the last little piece of this chapter before we move on to the other chapters. Okay, so we said that we could measure the enthalpy of a reaction using calorimetry, but there's 3 other methods of directly determining the enthalpy of a reaction, besides directly measuring it with calorimetry. So we can figure out the delta H of a reaction using Hess's law, where you add up a bunch of known reactions to equal your desired reaction. You can also figure out the delta H of a reaction using heats of formation, and it looks like this. The sum of the mole of the heat of formation of the products minus the sum of mole times heat of formation of the reactants. That's it. It's a very easy thing to do. You look up these heats of formations on a table. So if you were given like H2 plus O2 makes water, I'm going to show you an example problem, just in case he throws one on there, right? H2 plus O2 makes water. First, we have to balance the equation. So 2, 2. Okay, it's balanced. And then we look up on the table and let's say, well, the heat of formation of elements is 0. So the table, you wouldn't find them in their elemental form. So the heat of formation of elements is 0. And the heat of formation of elements is 0. So these two guys are in their elemental form. And let's say water, the heat of formation of water in the liquid form, because the state of matter matters, is 283 kilojoule per mole, right? So these values would come from a table. And the question would be, what is the heat of this reaction? So you look up the heats of formation and you do products minus reactants, you add them all up. So here's our product, 283, and we have 2 moles. So the heat of reaction would be equal to 2 times 283 kilojoule per mole. And then both of the reactants are 0. So that would be minus 0 plus 0. Because this epsilon means sum. That means add them all up. So the answer would just be simply 2 times 283 minus 0. So that'd be 566 kilojoule per mole. And the sign matters. So if the heat of formation is negative, you would have a negative sign there and you would put that in your problem. But this one, I'm just making up numbers, it's positive. Okay, so that's the first, so the first way to indirectly measure enthalpy is Hess's law. The second way is heats of formation, and the equation looks like this. And then the third way is bond enthalpy data, which is, the equation is going to look just like the heat of formation. So this was an example. The third way is using bond dissociation enthalpy, or just called bond enthalpy. So the heat of reaction is equal to the sum of mole times bond enthalpy for the bonds broken, minus the sum of mole, N is mole, the bond enthalpy data of the bonds formed. So it's bonds broken minus bonds formed. And you get these BE values, bond enthalpy data, from a table. So you just plug the numbers into this equation, and that's how you calculate the enthalpy of a reaction. And that's the flavor that he has on the exam. So let's do that last question using this. Bonds broken minus bonds formed. And it's a little difficult. I think this is the most difficult way because you have to be able to draw the Lewis structure so you can see which bonds are broken and which bonds are formed. You would never be asked to memorize a table. That would be crazy. Here we go. Let's do it. Let's do it. So our goal here is to correctly draw the Lewis structure, right? And this is what he gives us. N2 plus H2 makes ammonia. Right, correct. No Hess's law, indeed. Okay, so N2 has a triple bond between it. You would need to know how to draw the Lewis structure for that. And then we have 3H2. H2 has a single bond between it. And then we make 2NH3s. And this is what ammonia looks like. So again, it's really important that you can draw the Lewis structure because we need to know what bonds are being broken and what bonds are being formed. Okay, so he tells us to go to an appendix in the textbook. We will do so. We're not afraid of that. We can go to an appendix in the textbook. We can look at an appendix and not be scared about it. But you know what I'm afraid of is how to get to the textbook. That's what I'm afraid of. Would this get me to the textbook? Will that get me to the textbook? Yeah, that'll get me to the textbook. All right, appendix. Appendix 4, table A4.1. Appendix 4, table A4.1. Does somebody have these values? Lewis is a chemist that came up with the Lewis structure. Dang. I don't know if I can get to the appendix in the way that e-text is. Huh, table of contents. Appendix 4. Look at me go. Bond energy. Holy shit, I found it. All right, so we are looking for N3. And here is our bond energy data. I'm teaching Chem 10 at Merced College, not at UC Merced. You're welcome to take Chem 10 with me at Merced College. I always over-enroll. All right, so N3 is 945 kilojoule per mole for N3. So 945 kilojoule per mole, that's the bonds broken, right? We break the bonds in the reactant. And then bonds formed. So now I'm looking for an HH single bond in my stuff here. And I see it's 436 kilojoule per mole. So that's 3 times 436 kilojoule per mole. Okay, so it's delta H of the reaction equals the sum of bonds broken minus bonds formed multiplied by their mole value. I don't know why I started to rewrite the equation. So that's 3 times 436 plus 945. Okay, minus bonds formed. So this is this value and this is this value. Okay, and now look at how many bonds we're forming. We're forming 1, 2, 3 NH bonds times 2. So that's 6 NH bonds. So 6 times NH bond. And an NH bond is 391. So 6 times 391. So that's what goes right here. 6 times 391. Yeah, there's one question like this. Nope, you assume all the bonds break. You assume all the bonds break in the reactants and all the bonds form in the product. And yeah, Vivi, there's one question like this. I should make a structure called the dusty structure. I agree. Okay. All right. So the equation is the sum of bonds broken minus the sum of bonds formed. So the reaction was N2 plus H2 makes NH3. And that's a 3 here, and that's a 2 here. So I drew the Lewis structure for N2, here it is. And then I drew the Lewis structure for H2, here it is. And then I drew the Lewis structure for NH3 so that I can see what bonds are forming and what bonds are breaking. And then I went to the textbook and I went to the appendix and I am now looking for these values. So the N333 bond is here at 945, and that's how I got that number of 945. And then I looked at the single bond HH number, 436, and that's how I got this number right here, 436. And there are 3 of those bonds being broken because of the balanced chemical equation. So that's 3 times 436 plus a 945. Those are my bonds broken. And then my bonds formed are 1, 2, 3 NH bonds times 2. So that's a total of 6 NH bonds. And my NH bond has a value of 391. So that's how I got this 6 times 391. Okay, I'll put this in my calculator now. So the answer is negative 93 unit from the table is kilojoule per mole. All right, so that's one question on the 22 question exam, and that's the end of chapter 10. Okay, let's do chapter 9. Yeah, there is a question like this on the exam. No, Anna Luz, there is a question like number 1. Yeah, indeed, indeed. So the questions that I went over are the ones that are on the exam. Yeah. Yes'm, yes'm, yes'm. Okay, chapter 9. Here we go. Here we go. Chapter 9. Chapter 9. Chapter 9 is gas laws. I think it's easier. I think probably chapter 10 is the hardest. Oh, I was already here. I was already here. Here we go. Here we go. Okay, gas laws. So let's review that business like this. I will show you the concepts and equations of chapter 9 using this. No, this. No, this. Okay. All right, we've got the main equations of this. A little bit thicker. Probably need to like zoom in or some shit. I don't know. So the main equations of this are the ideal gas law. Correct. I went over all questions except question 4D. That is correct. All right, so you've got the combined gas law, P1 V1 over T1 N1 equals P2 V2 over T2 N2. So this, when do we use this one? When a change was made to a gas. So combined gas law. And if no change was made to the gas, you don't use this one. So you got to read the question to know when to use what equation. And we want to make sure that our temperature is always in Kelvin in the gas law chapter for sure. And then of course we have the ideal gas law, PV equals nRT. And R governs what all the units should be. R equals 0.08206 ATM time liter over mole times K. So that means pressure always needs to be in ATM, volume always needs to be in liter, temperature always needs to be in Kelvin, and of course moles is moles, right? So those two you need to be ready to use at any time. Now with the combined gas law, if a certain variable isn't given in the problem, you simply take it out. So I'll show you how to use both of these before I move on to other concepts. Okay, let's look at this. All right, so we're gonna focus on 4. I'm gonna backtrack to the other problems, but we're gonna focus on 4. And 6. Okay, in some cities, public buses are fueled by compressed gas. How many grams? Okay. The question wants grams. That's the first thing whenever I try to do word problems, I'm like, what the hell does this question want for me? Oh, it wants grams. Okay, okay, okay. How many grams of CH4 are in this volume? Okay, I have a volume. At this pressure, I have a pressure, and this temperature. Assume that the gas behaves as an ideal gas. So this is easy. I know I'm triggered in my head that I'm going to use, I have a 1 volume, 1 pressure, 1 temperature. So I'm going to use this equation, not this other equation where I need 2 of something to start using it. Okay, so I'm not going to work it out because I want to get through all the things, but you're going to use this. And you're going to solve for N, and then you're going to turn that into grams with the molar mass of CH4. Okay? And don't forget to turn your temperature into Kelvin and your pressure into ATM. So you're going to solve for N and turn it into grams. Okay, number 5. A gas has a total volume of this and contains different molecules. So that's going to be the partial pressure of a gas. That's not the 2 equations that I'm trying to show you. How do I know that? Well, it's got the word partial pressure and it has more than 1 gas. So this is partial pressure of a gas, and we'll come back to it. Let's look at 6. The pressure inside a weather balloon is released. Okay, I have a pressure. If the volume and temperature of the balloon are this, okay, I have a volume and I have a temperature. What is the volume? Oh, boom, I have a second volume. So now I know I have a pressure 1, a volume 1, and a temperature 1. And I need volume 2. When it reaches an altitude where its internal pressure is this, so I have a pressure 2 and I have a temperature 2. It does not, so I know I'm using my combined gas law. It does not include moles, so I take it out. That's why we like the combined gas law. If something is not included in the problem, you simply take it out of the equation. So the equation becomes P1 times V1 over T1 equals P2 times V2 over T2. So I can solve for V2 already. I bring T2 up, I multiply by T2, and I bring P2 down. I divide by P2. So that means V2 equals T2 times P1 times V1 over P2 times T1. It's very easy to mix all those up, so make sure you did it correctly. And then you just plug everything in. Turn your temperature into Kelvin and everything else can stay like it is. We only need to be in ATM or liter whenever we're using the ideal gas law because of R. But if we're using the combined gas law, we can be in whatever units it gives us, except for temperature. So make sure you turn your temperature into Kelvin, and then you solve for volume. Okay, so that's the two main equations of the chapter. Now I'm going to show you how to deal with the other problems and the conceptual stuff that you need to understand. So the big things to understand is what affects how fast a gas moves. So the rate of effusion. Effusion just means a gas leaking out of a hole. And the higher the temperature, the faster the gas moves. And the smaller the gas, the faster the gas moves. So I'm going to show you two things now in the PowerPoint. So the higher the temperature, the faster the gas moves, and the smaller and lighter the gas, the faster the gas moves. And that makes sense. Use your intuition. So the less dense the gas, the higher rate of effusion. The higher the temperature, the higher rate of effusion. The lower the molar mass, the higher rate of the effusion. So that's lower molar mass means faster. Higher temperature means faster. Lower density, because that means a lower, it's not as packed together. It's gonna effuse faster. But I want you to focus on this root mean squared situation, and we're gonna use that for number 3. And that's also going to help us answer number 1 as well. So he's got root mean squared in 3 different problems here. So we are giving it our respect. So let's go to the PowerPoint now and look at what the hell is root mean squared. It's how we measure how the rate of effusion of gases. That's what root mean squared is. Oh, I probably have it here. Yeah. Okay, so we are focusing on what the heck is root mean squared? What do we need to know and what do we do with it? Here it is. So Graham's law is relating the rate of effusion with the molar mass. So the smaller the gas, the faster it's going to move. And here is your relationship between molar mass and rate of effusion. So this is our focus right here. So if you're comparing the rates of effusion of two gases, that's the equation that you're going to use. So the rate of effusion looks like this. That's the symbol for rate of effusion, and it has a formula. I'll show you the formula. It's like 3RT over molar mass square root. That's the formula. But if you compare the rates of two gases, then you're using this, which is Graham's law. So the root mean squared, the ratio between the rate of effusion of two gases is equal to the square root of the ratio between their molar masses. But you have to, the denominator of one is the numerator of another. So I think you should know how to do this problem here. And then also I want to show you how to calculate this, the root mean squared. So be familiar with this problem here. Slide 7. And he has an example here, which is another good one to look at, right? He's got two examples, so you definitely want to pay attention. And then he's got 3 different questions on the study guide that's focusing on this. So here we are with the root mean squared actual equation, right? This up here is the ratio between the root mean squared. And this right here is how to actually calculate the root mean squared. So a few things to take note of. R is different here. R is now 8.314 kilogram time meter squared over second squared times mole times K. Yes, that is the whole S unit of R. You're going to be all right. Don't freak out. And the capital M is molar mass. So now let's go back to the study guide and use this equation. I believe we have to calculate this equation using this equation. Okay, let's see how this works. So rank the number 1, rank the gases in order of increasing root mean squared. So it's going to be lowest molar mass to highest molar mass. So they're already ranked. They're already in the proper order because of the molar mass. So this one is already the lightest. This one is already the lightest, and this one is already the heaviest. So they're already in order of increasing root mean squared. And then for number 3, we're going to use that other equation. So the root mean squared of gas X versus the root mean squared of gas Y equals the square root of, we don't have to use that equation, so we're good. We're going to use this other equation. I'm doing number 3 right now. So these are already in order. NO, NO2, N2O4, N2O5. Oh, it needs to go the other way. Increasing speed. My bad. So I just need to change these boys around. Boop, boop, boop. So this is going to effuse the fastest. And this is going to effuse the slowest. All right, so here we're molar mass of Y over molar mass of X. And he's saying that this equals 4. And it's saying that the molecular hydrogen effuses 4 times as fast as gas X. So we're going to say H2. And then up here, this is going to be the molar mass of H2, which is 2.02 gram per mole. So now we know the square root. So this equals 4 because it tells us. So this is 2.02 gram per mole divided by the molar mass of X equals 4. And so now I square both sides to get rid of the square root. So that's 4 squared. So it's 16. So now we have 2.02 over the number we want equals 16. And then solving for molar mass, I bring molar mass up and 16 down. Oh, wait, sorry. I have made a grave error. I got to switch this around. This needs to be here and this needs to, one moment, let me fix. This is H2 and this is H2 and this is the molar mass of X. Okay, that's how it should look. Now I will switch my numbers around here and here and here. There we go. So this is molar mass of X and this is 2.02, which is the molar mass of H2. Okay, now it is what it's supposed to be. So now 16 times 2.02 molar mass of X equals 32.32-ish. And I can tell you, I already know what gas it is. It's O2 because that's the molar mass about the molar mass of O2. So that is how you handle this question. You got to know how to use this equation. He doesn't have the other one on here, which is to directly calculate the root mean squared. So we don't need to worry about it. We don't need to worry about this. All right. Let's look at, we're going to skip 5. We don't need to worry about partial pressure, but we're going to look at 7. And then we'll be done with chapter 9. Oh, my bad. I was not sharing that, huh? Okay. Yeah. I don't know. Maybe it is sulfur. I'll do it again. Yeah, I was not sharing properly. That's my bad. I will do it one more time. Quickly now. Quickly. I got to share my screen so I don't do that again. Okay, back to it, real fast. Here we go. Root mean squared. Of H2, because that's what we have in our problem, H2, over root mean squared of X, we want gas X, he says is equal to 4. I don't know, it might be sulfur. Because, well, let's talk about it. Let me find that answer again, and then we'll talk about why it's probably oxygen, but we'll see. So this is going to be equal to the molar mass of X, the gas that we want, divided by the molar mass of H2. So that means, so this value equals 4. So 4.00 equals the square root of the molar mass of the gas that we want divided by the molar mass of H2, which is 2.02 gram per mole. So I square both sides to get rid of the square root. So 16 equals molar mass of X times 2.02 gram per mole. It might be sulfur. Yeah, I guess it probably is sulfur. 16 times 2.02, 32.32. Yeah, no, that's not going to be sulfur because sulfur is 32.064. So the molar mass I got is 32.32. I'll use super accurate hydrogen. 1.00794 times 2. 2.01588 times 16. 32.25 if I'm being super accurate. So that's heavier than sulfur. 32.25 gram per mole. So if we had to guess at the identity of the gas, I'm going to guess oxygen because oxygen is 15.9994 times 2, which is 31.9988. That's, yeah, I mean, that's not exactly what it is, but it's okay. He didn't, oh, we could say it's phosphorus. No. Yeah, I would be torn between O2 and sulfur. I would be torn. But he doesn't ask us the identity of the gas, so that's good. So this is not a hard problem. You just have to know how to use the equation and what the equation is. Okay. We're looking at number 7, and we are not worried about number 5. But we were worried about every other question besides number 5. So now let's do number 7 and we'll be done with chapter 9. Okay, number 7 is definitely something to worry about. As stated, number 1 through 3 are all dealing with root mean squared. So obviously we care about root mean squared. We have 1 partial pressure of a gas, number 5. We're not going to worry about it. Number 7 is gas stoichiometry. And it's not hard because we understand stoichiometry, so we can handle it. And I'm going to switch to maroon. Okay, how many grams? Let's figure out what the hell this thing wants. How many grams? Oh, it wants grams of this boy. Okay, cool. So how many grams of him do we need to generate this volume at this pressure and this temperature? Oh, that sounds like we need to use PV equals nRT of oxygen. So I'm going to go from moles of oxygen into moles of KClO3 into grams of KClO3. So I need to find moles of O2 so I can find moles of KClO3 and then grams. To go from moles of O2 to moles of KClO3, that's going to be the mole ratio coming from the balanced chemical equation, of course, which it's already balanced for us. And then to go from moles of KClO3 into grams, that's the molar mass. But now, how the hell do we find moles of O2? The ideal gas law, N. We need to find moles of O2 with N. We have to memorize these formulas. Yeah, we have to memorize these formulas. All the heat capacity, all the chapter 10 formulas have to be memorized. All the formulas have to be memorized for the most part. Okay, so let's do it. We're going to find N. So N equals P times V over R times T. You don't have to memorize anything for the final. Everything's given on the final. Just have to know how to use it. All right, so plugging in our pressure, we're in the unit of ATM, so that's good. We're chilling. And then volume is already in liters. That's good. 200.0 liters. And then R is 0.08206 ATM time liter over mole time K. Temperature is in Kelvin, so cool. We don't have to convert anything for this problem. That's very nice. ATM goes away, Kelvin goes away, liter goes away, so I'm left in mole, which is what I want. So I would recommend you put this into your calculator so that you can make the common mistakes that students make, and I can show you how not to make that mistake. So the correct answer right here is 7.5885 moles. But if you did it wrong, yes, the conversions will be given. Yes, but not the formulas. Good question. But if you did this question wrong in the calculator, then you got if you did it wrong in your calculator right now, then you got this number. That is not the right answer. This is the right answer. And it's probably because you put a multiplication in your calculator. But that's not what's happening to the temperature. It's being divided by the original value you put in. So that needs to be a division in your calculator. If you absolutely want to put a multiplication, then you need to put this in parentheses down here so your calculator can follow PEMDAS. Okay, so we found our moles of O2. Now we're going to turn it into moles of KClO3 and then mass, and then we'll be done. So this is gas stoichiometry. We've taught you how to find moles in 3 different ways. To go from grams to moles, you use the molar mass. And then to go from molarity to moles, you use the volume. And now to go from gas information to moles, you use PV equals nRT, and that's it. Those are the only 3 ways that we turn things into moles. So here we are using the gas one. All right, so our moles is 7.5885 moles of O2. We're going to turn it into moles of KClO3 with the mole ratio from the balanced chemical equation, 3 to 2. There's 3 moles of O2 for every 2 moles of KClO3. And now I need grams because the question wants grams. So I'm adding up my molar mass of KClO3. That's 1 potassium plus 1 chlorine plus 3 oxygens. So I've got 122.5492. And if I was taking an exam, I would add that up twice in my calculator. I would add it up in my calculator until I get the same number twice. I'm always checking my work on exams because I'm trying to get an A forever. And I'm always trying to get the highest grade in the class. It's like shoot for the stars so you can fall somewhere between the earth and the stars, you know, all that shit. All right, so we've got our moles times 2 divided by 3 times my molar mass. The answer to the question is, well, let's see how many sig figs. 2 from the pressure. So my answer is 619.97 grams KClO3, but I need 2 sig figs, so that's 620, no dot, grams. Okay, that's the end of chapter 9. Chapter 8. Here we go. I think chapter 8 is not that bad. That's why I'm going to do it, even though we've been going for almost 2 hours. I'm still going to do chapter 8 because it's not that bad. It could be worse, and I feel like he's taking it pretty easy on you guys for chapter 8. These are, and I'm going to go over every single question because they're all on there. The concepts of these guys are all on there. He doesn't have you do the hard stuff of the chapter. He doesn't have you do net ionic. He doesn't have you balance a redox equation in basic or acidic media. So that's cool. That's cool. All right, let's do chapter 8 and get out of here and move on with our life.
Dusty, since we're not given for us to do the net ionic, is he going to give us the net ionic equation and it's like a multiple choice for us to choose or to know what's going on?
No, he doesn't test you on determining the net equation, the net ionic equation. It's just not, that concept is not on there.
At all? Oh,
Yeah.
okay.
Yeah.
So for like question number 5,
Yeah.
is that one on there then?
Mm-hmm.
So just knowing the oxidation rules, pretty much?
Yes. Correct. Yes.
Okay. Thank
Yeah.
you.
Yeah, you're welcome. And let's talk about it. All right. So this chapter is governed by your understanding of the unit molarity. So we have to be comfortable with molarity. And now I'm going to switch to back to green, I guess. So molarity equals moles of solute over liter of solution. So if you want to find moles, you do liter times molarity equals moles. And you have to do that quite a bit, right? Another thing that you need to be comfortable with is the dilution equation, and probably you already are, and I can't talk. Like eventually if you talk a lot, well, for me anyways, I start to like mess up talking, and I can tell I've gotten to that point. Like I'm not gonna be able to talk correctly anymore. Okay, so this is the dilution equation, M1V1 equals M2V2. The words that need to trigger this are stock, initial, and this over here is final. This might be concentrated. And this might be diluted. So you see any of those words and you're like, okay, dilution equation, here we go. You don't have to have your volume in liter using the dilution equation. If you're asked to find molarity, you just simply need to find the moles and divide it by the volume. So this is kind of everything we need for all the questions up to number 5. So let's do it. Tap water in North America is this 48 milligram per liter. Okay, that's a concentration, right? What's the molarity? Okay, that means we need moles per liter. And I'm given milligram per liter. So that's easy. I just need to turn milligram into moles. So 48 milligram per liter. I'm going to turn it into grams so I can turn it into moles. There's 1,000 milligram in 1 gram. And now I need the molar mass of calcium. It doesn't matter that it's calcium 2 plus because electrons don't count in the mass of an atom. So we don't care if we're missing electrons. That's not going to change our mass. So we've got 40.08. That's the molar mass of calcium. So 40.08 gram per 1 mole. And of course, the liter unit is still there. It's still there on the bottom. So milligram goes away, gram goes away, and I'm left in mole. And that's how you solve for this. 48 divided by 1,000 divided by 40.08. Ooh, 0.00. I need 2 sig figs. So that's 1, 2 mole per liter, which is what molarity is. Of calcium 2 ions. Done. Next. Chemists who analyze sample for dissolved trace elements may buy standard solution. Oh, I should put standard over here as well. Solutions that contain this concentration of the elements, okay? Actually, standard belongs on this side. This is because you usually make a standard. But it kind of depends on how the question is worded. If a chemist needs to prepare. Okay, so when we see the words prepare, we know we're going to do a dilution. So let's try to identify everything. This is like the hardest worded word problem of dilution I've ever seen. So a chemist needs to make this volume. So if we made something, it's over here on the final side. So that's V2 of a working standard that has a concentration of this. So we need to make this concentration. That's M2. Over here is the thing that we made. Of a working standard that has a concentration. What volume of this standard is needed? So what volume of this standard? So we're looking for V1 and our standard, oh my God, fine. I'm putting standard on both sides because it can be on both sides. Our standard is 1.00. M1. So I found all of the players of the game, but it was kind of hard. Now let me show you a concept check here that can help you to make sure you've identified your players properly. M2 is going to be a lower value than M1 because it's diluted. So it's going to be a less concentrated situation. So M2 is 5.0 milligram per liter and M1 is 1.0 gram per liter. So this is more concentrated, right? So we know we properly found our M1. And we want to know what volume of M1. So we're definitely finding V1. All right, so we're finding V1. So V1 equals M2 times V2 over M1. So M2, well, we have to have our molarities be the same unit or else we can't divide them by each other, right? So I'm going to turn my 5 milligram per liter into gram. There's 1,000 milligram in 1 gram. So that'll turn me into gram per liter. That matches my other value because we can't divide numbers that have different units. I don't know why I'm putting this in my calculator. I think it's because I'm getting tired. So we've got 0.00500 gram per liter. So that's M2. And we can see that it's a smaller concentration than M1 as M2 should be. And then our volume 2 is the one we want to make. So that's 0.500 liter. And then we divide it by M1, which is 1.000 gram per liter. And those two units go away and we're going to be left in liter. So times 0.5 and my volume is 0.0025 and I need 3 sig figs. Yeah, so 0, 0. That's how much of this standard solution we need. So yeah. Usually M is, that's a good question, and I will explain. Capital M is molarity, not mass. Lowercase m is mass. And I agree with you that the unit of gram per liter is a density, but we can still use the unit of gram per liter as a molarity because the units are canceling off. Now, if we were asked to find molarity and we were given like an M1 of gram per liter, we would definitely turn it into mole per liter. But that's not necessary because the units go away and we are just left with liter. Good question. So the question was, why am I calling gram per liter a molarity when clearly it's a density? It totally is. But it's just the way we're given concentration in the volume or in the problem. We are given the concentration and density, and we're just treating it like it's a molarity because the units will cancel off. So we don't have to go through that extra step of turning our gram per liter into mole per liter because the units cancel out. But again, if I was asked to find like M2 and my M1 was in gram per liter, I would turn it into mole per liter because then my units wouldn't cancel out and I would be left with a unit of gram per liter. And I would need to turn it into mole per liter. Good question. All right, let's check out 3 and 4. I'm just going to do 3A and 4A. No reason to do both. Okay, so 3 says, how many grams of solute? Well, I know how to find that because I have a molarity. If I have a molarity, I can definitely find grams because molarity is moles over liter. So I will turn that moles into grams and call it a day. I'm going to erase my work. Okay, so how many grams of solute? So I need moles, right? We need to go from moles into grams. And I have volume and I have molarity. So I need to turn my volume into liters so I can multiply it by molarity. 1, 2, 3. Because I'm doing this thingy right here. So I have 0.2500 liter times my molarity, 0.125 moles per 1 liter. That's what capital M really looks like. And now I just need the molar mass of copper sulfate. I will add that up. I have 1 copper. Plus 1 sulfur. Plus 4 oxygens. Okay, so that's 159.6016. I'm using a periodic table that's hella extra and it has 4 decimal places. So liter goes away, moles goes away, and I'm left in grams of copper sulfate. I put it in my calculator wrong, so I had to start over. All right. So we have, how many sig figs? 3 from the molarity. 0.499 grams. All right, B is done the same way. Let's look at 4A. How many milliliters are required to neutralize? That means that's just another word for turn this from moles of the thing given into moles of the thing asked. How much stuff is required to neutralize? So we've got an acid and we've got a base. So we need to make sure they're in a 1-to-1 mole ratio. If they're not, then we need to use their proper mole ratio. So we're going to go from volume of acid into moles of acid into moles of base into volume of base. This is a titration problem or just a regular acid-base problem. So to go from volume of acid into moles of acid, we use the molarity of the acid. Then to go from moles of acid to moles of base, you use the mole ratio. That's why we need the balanced chemical equation. Then to go from moles of base to volume of base, we use the molarity of the base. So it's a three-step problem. But first, we got to set up a balanced chemical equation so we can get that mole ratio between them. So we've got HCl and sodium hydroxide. And they are going to make sodium chloride and water. Yes, you need to know how to do a simple double displacement predictive product so that you can get the mole ratio, or you can just understand that if you only have one hydrogen in your acid and one hydroxide in your base, they are in a 1-to-1 mole ratio. If we had like H2SO4 with calcium hydroxide, they are also in a 1-to-1 mole ratio. But if you had H2SO4 with sodium hydroxide, they are in a 2-to-1 mole ratio. So you can either understand what I did over here, or you can do the balanced chemical equation. Okay, so this equation is balanced. So they're in a 1-to-1 mole ratio. So the work looks like this. You start off with the volume of acid. It's in 10 mils. We need to turn it into liters because we're going to multiply by the molarity. So 1, 2, 3. So that's 0.0100 liter times the molarity to get to moles. 0.0500 moles HCl per 1 liter. And here's where the mole ratio comes in. There's 1 mole of HCl for every 1 mole of sodium hydroxide. But if you don't understand how to create the balanced chemical equation, you can just do H plus for OH. So if we were doing the sulfuric acid and sodium hydroxide up here, that would be 2H plus to 1 OH. That's how you figure out the mole ratio real fast. Okay, so liters of acid goes away, moles of acid goes away. I'm left in moles of base, and it wants molarity. Oh no, it wants milliliter. Okay, so now I need the molarity of the base, which is 0.100 moles of base is equivalent to 1 liter. And then it wants milliliters, so I need one more step of 1,000 milliliters in 1 liter. So moles goes away, liters goes away, and I'm left in milliliters. Okay, so in my calculator is 0.01 times 0.05 divided by 0.1 times 1,000. So this is 5 milliliters is all I would need. That's the answer. And the sig figs is 3. So 5.00 milliliters of the base to neutralize the acid. Okay, we only have one more problem to do, number 5, which is redox. And for that, you do need to memorize the oxidation rules, but they're not that bad. So I will erase the board and do the last problem of the day. It's only 5:09, not too bad. Not too bad at all. Okay, board is getting erased and we're going to talk redox. All right, let me tell you the oxidation rules. Last vibe, yeah, my dogs are freaking out. Is gonna be black? Fine. Okay, here's the oxidation rules. They're easy. Oxygen is -2. Elements are 0. Hydrogen is +1. I swear that's all you need. I swear. And those are not always the case, but I think you'll be good with these. You just need to know how to use them. Oxidation rules. Of course, there's other rules like the charge that you see above an atom is its oxidation. And oxygen is sometimes -1 when it's in a peroxide. And hydrogen is sometimes -1 when it's paired with a metal. Group 1 metals are +1, group 2 metals are +2. So I would not trust me, and I would look at the actual long version of oxidation rules and commit those to memory because I'm trying to be an A+ student. But if you're being lazy and you're trusting me, those are the rules you need. I swear you'll be okay. All right, but you need to understand what I mean by elements are 0, and a lot of students don't. If a thing is in its elemental form, it's all by itself, and you don't see a charge, it's 0. All right, so let's read this problem. A nail is made of iron. Well, that's in its elemental form. See how it's all by itself and it doesn't have a charge? So that's 0. It's placed in an aqueous solution of soluble palladium 2. So that's this, palladium +2. And if somebody tells me it's aqueous, then I'm going to put aqueous as my state of matter. And it's +2 because it says 2. So I didn't even need to figure that out. It gradually disappears as the iron enters the solution as iron +3. Okay, so now the iron has turned to +3. And palladium metal, back to it being palladium metal. So that's palladium in its elemental form. So this is elemental palladium, not ionic palladium, like palladium +2. And this is elemental iron, not ionic iron, like iron +3. And then he just says, balance the equation. Well, it's balanced. There's one of everything. What are the oxidation numbers of the different atoms in the reactants and products? Well, that's it. 0, 2, 3, 0. Let's see who was oxidized, who became more positive. Iron. Iron was oxidized. It became more positive. And if it's oxidized, yeah, you're going to have to balance it on the text. Then it's the reducing agent. And then, and I'll show you how to balance it right now. Because when he says balance the equation, he means the full equation and all the electrons. So I'll show you how to do that. And then who became more negative? Who went down who went to the right on the number line? Reduction is down. Palladium, he went from +2 to 0. So he was reduced. And if it was reduced, then it's the oxidizing agent. All right, so now I'm going to go to another screen and show you how to balance the equation. Then we will be done for real, for real. Okay, so we want to know how to balance this thing. And there's a long version, but he's not asking you to know the long version. So I'm gonna show you how to do the long version, but we're gonna see that this is an easier, or this is a shorter version. I'll just say it like that. Okay, so the steps are determine species oxidized and reduced and write the half reactions for that. So really write half reactions. And what you do is anybody who was oxidized, a little bit thicker, just a little bit thicker, just a little bit, okay. Anybody who was oxidized needs to come down into the oxidation half reaction. So iron was oxidized, so then we write the half reaction. You just bring down anybody touching the species oxidized, which is just itself. Okay, and then we need to do the reduction guy. That's the one that became more negative. And that's anybody touching the one that lost or that gained electrons that became more negative. And that's palladium. So we wrote our half reactions. Second thing you do is you balance all atoms other than hydrogen and oxygen. So you don't balance hydrogen and oxygen like normal. And you do that to the half reaction. So our half reactions are already balanced. I have one iron on the left and one iron on the right. And then with palladium, I have one palladium on the left and one on the right. So I'm chilling. And I don't even have any hydrogen and oxygen. So that's what I'm telling you. He's asking you the easy version of the question. He's not even having you balance hydrogen and oxygen, which is nice. Okay,
So in the test, we're not given oxygen or hydrogen?
right,
Okay.
right. But I'm going to pretend like we do have them just to show you the complete situation here. So for step 3, you balance any oxygens, balance oxygen with water. So you bring in water molecules to balance any oxygens that you might have, which seems weird to bring in a whole molecule, but that's what you do. You bring in a whole water molecule, as many as you need. And then after you balance oxygen, you balance the hydrogens using H plus. But we don't have oxygen or hydrogen. So this is the order. First, you do all atoms other than hydrogen and oxygen. Then you do oxygen, then you do hydrogen. Now we're going to actually have to start doing something. Now you balance electrons or balance charges with electrons. And if the species is oxidized, and I'm gonna share my screen and take off some of this stuff so I can move stuff around. So here we are. We're like this. We're like this. Okay. So if the species is oxidized, that means it became more positive. That means it lost electrons. That means electrons are products. You need them to be on the product side. And so we just balance our charges that we see. The left side is 0. It doesn't have a charge. The right side is +3. So I need them both to be balanced. And I can only bring electrons into one side. So the only way to get that 3 to go to 0 is to add 3 electrons. And now I've added 3 negative ones, so it goes to 0. So I have balanced my charges with electrons. And then for reduction, because the thing is being reduced, electrons are reactants. So I've got a +2 on the left and a 0 on the right. So I need 2 electrons to balance off my +2, and that goes to 0. The next thing I do is I balance electrons by making them equal across the equation, across both of the half reactions. So I've got 2 electrons for reduction and 3 for oxidation. The only thing I can do is multiply them by each other to get them to equal the same. I need them to be the same. So that makes everything be times 3. So this is now 6 electrons. And this is now 3 palladiums and 3 palladiums. And then on the top, this is now 2 irons, and 6 electrons. And then I can finally add my reactions together. If you did everything correct, your electrons will go away. You should never have electrons remaining. And you just write the remaining species, and this is the equation balanced, and this is the end of the process. If he were to ask you how many electrons were transferred, the answer is 6. It is not 12. You don't add the electrons together. All right, guys, good luck. I will see you next week for the final exam. I'll be there walking around staring at you. Yes, you're welcome. Good luck. Bye.
Yes, Dusty, I have a question.
Go
Will
ahead.
you be doing a final exam review for next week?
Well, that's kind of hard because it's the entire semester. It's the entire semester. The ACS is really hard. So I'm just going to hold extra office hours on Zoom, but I can't go over a whole semester. So it won't be like this, but I will be on Zoom helping. Yes.
Okay, thank you.
You're welcome.